Okay, so here we are. Gonna try to knock out this chapter all in one video. It's a short chapter, short little bit of stuff to do. So we'll see if we get it done. If it's stretching on past, 15 minutes or so, then good, we might break it up, but we'll try to get through it in one. So what we're covering today, we're kind of picking up a little bit where we left off. We've been talking about respiration, ventilation, really. But the process of getting respiratory gases into the blood, right? And now, of course, we need to have more bulk flow, right? In this case, we're going to do so through what we're going to call circulation, which is going to be the next chapter. But before we get into that, we need to understand how these respiratory gases physically travel. And for oxygen, that's a bigger problem than you might imagine, right? If you remember from the last series of videos, one of the things we talked about with water, which is what most bodily fluids are made of, is that it doesn't really hold a lot of oxygen, right? Carbon dioxide will go into it pretty okay, right? But oxygen really doesn't go into it. And so what we're going to find is that we need to have a series of what we'll call respiratory pigments, right? And we'll talk about what some of these pigments are, right? Just in case YouTube's caption algorithm doesn't work very well for us. Pigments. And so the one we're most familiar with here probably is the one in our blood, which is hemoglobin. And hemoglobin in mammals here is built on this sort of 4 protein chain arrangement, 2 of these alpha globins, 2 of these beta globins, and each of which has an iron stuck in the middle of it, which is what this guy right there is. And we'll talk a little bit more about hemoglobin specifically moving forward. But there's a related pigment that we talked about a little bit, off and on, scattered throughout the chapter, and that's myoglobin. And myoglobin and hemoglobin do basically the same thing, right? They're there to bind oxygen so we can transport it or carry it or whatever, right? We can get it into an aqueous solution. But with myoglobin here, myo, of course, means muscle, right? So myoglobin is associated with muscles, and it is only a single globin chain. It's not 4 like hemoglobin is. So the oxygen storage capacity of myoglobin is 1/4 that of hemoglobin. Now, there are going to be some other pigments that we'll come across. We'll talk about those in a couple of slides. These will be hemocyanins, hemoerythrins, chlorochlorins, so on and so forth, that exist in different lineages of animals. Not everybody has hemoglobin, but they all have the same basic fundamental problem, right? Getting oxygen into an aqueous solution. One other thing that we have to cope with, I guess, as mammals is that for at least part of our lives, we are not responsible for our own oxygen collection, right? We get our oxygen from mom. And one of the challenges there, right, is that by the time mom's blood gets to us, right, and these things are supposed to cross the placental barrier, some of that oxygen's already been pulled off, okay? And so we need to have kind of sort of like an oxygen magnet, hemoglobin. And that oxygen magnet hemoglobin is made simply by changing out one of our globins for a different kind. So we make what's called fetal hemoglobin using alpha globin and gamma globin, okay? And the combination of these two, again, it has a very high affinity, very readily bonds or binds oxygen, and has a harder time letting it go, right? And this is really important for us because, again, we're trying to forcibly remove oxygen from somebody else's blood supply, right? We are very much parasitic in that sense. But once we get out, that's not good, right? We need to be able to not only bind oxygen, but to let go of it. And we want to let go of it easily. So we stop producing fetal hemoglobin, right? And we do so by tailing off our production of gamma globin and ramping up our production of beta globin. And this is what we call hemoglobin A. Okay, so this is hemoglobin F for fetal, hemoglobin A for adult. And again, just a lowered oxygen affinity. Okay, so what we've got here is a phylogenetic tree, right? A family tree, basically, of different kinds of animals, going all the way down to sponges and comb jellies, and up to vertebrates, things like you and me down here. And what the little color coding here has to do with is what the primary respiratory pigment is in the blood. Okay, if we're here in red, okay, these are going to be hemoglobins. If we're in blue, so arthropods, mollusks, okay, we're going to have instead what's called hemocyanin. I'm going to write that out. So you probably can't read that on that tiny little picture, right? But hemo, right, and hemo just means blood. Right, so we have hemoglobin because our respiratory pigment is built on globin, okay, the protein globin. Hemocyanin, okay, and hemocyanin is so named because it's blue, right? Instead of having red blood, they have blue or cyan colored blood. And the reason that their blood is blue and our blood is red has to do with the metal ion that actually binds the oxygen gas to it. So in you and me, right, we talked about this, it's iron, right? Hemocyanin, the metal ion, is copper. It's not as good, okay, at binding up, at binding oxygen as iron is, but it works, okay. Sorry. The other major option that we see here, and we see this primarily here in annelids, so these roundworms, right, are chlororins, and chlorochlororin is here built not around not around a different metal ion, but a different structure. Okay, so the actual heme is a little bit different, and as a result, the color of the blood, instead of being red or blue, is green. So we've got those three different options here. Leave me alone. There's three different options here for means of trying to get oxygen into water, basically, which doesn't like to have it. There's also things called hemerythrins, which have no heme, and the iron is actually bound directly to the globin protein. Those are weird. They pop up in weird places. We're not going to worry too much about those. I'm not even going to write it out. When we look at the ability of whatever our respiratory pigment is to carry oxygen in blood, one thing we always need to kind of measure it against, again, going back to kind of Dalton's law, right, is, well, what's the partial pressure, right? What is the amount of oxygen in the blood? And we can measure that against two different sorts of things, right? We can talk about percent saturation, right, which is what, pull my laser pointer back, which is what this curve over here is. So of our heme groups, or of our whatever group, okay, how many of those have an oxygen bound to it, right? So for a single hemoglobin, right? It could be 1 out of 4, 2 out of 4, 3 out of 4, or 4 out of 4, right? 25, 50, 75, or 100%. But as we start to add those up, we can get, intermediate percentages in there. But basically the idea is that we have this sort of sigmoid or S-shaped curve, right? Where percentage saturation increases with partial pressure, but not linearly. Okay. The same basic idea over here is with how much actual oxygen gas is in the blood related to partial pressure. And again, the same thing is true there. A non-linear relationship to that. And this is called an oxygen equilibrium curve. Sometimes we call it I'll pull my pen back up here, a dissociation curve. And this is the term that we're going to use really most often here, dissociation, because this is why we have these curves. We want to know at what partial pressure of oxygen are we going to pick up oxygen and where are we going to drop it off, right? Where are we going to disassociate oxygen from the heme group or from whatever else. So if we look at a dissociation curve then, or a delivery curve, you can call it a delivery curve if you want to. Here just for arterial blood, the reason this becomes important, I think, eventually comes out, right? So here in this blue highlighted region of our dissociation curve, this is where partial pressures are high, right? And so we associate higher partial pressures here with, say, blood in the lungs, right? It's picking up oxygen, there's a lot of oxygen there. But as that blood travels around the body, right, it's going to encounter the tissues of the body that have used up some of their oxygen. And so their partial pressures are much lower, right? So say here at rest, or if we're really working hard or doing something really demanding, our partial pressures might be down here, right? And one of the neat things to kind of pull out of this, again, because this is a non-linear relationship, this curve is pretty flat here at the very end of it, right? As we near saturation, our dissociation curve is pretty flat, which means that we can lose a lot of oxygen in the body, right? We can use a lot of oxygen up in the body, but not get rid of a lot of oxygen from the hemoglobin, right? And so at rest, right, this reason it becomes important is we're gonna get there in a second. But at rest then, right, we're only gonna drop off maybe 1 out of every 4 oxygens, okay? We're gonna have continuously circulating around the body, even in venous blood, even in blood that's coming back to the heart that's supposedly deoxygenated, right? We're still gonna have about 3 out of every 4 oxygens stuck to that hemoglobin still, okay? And this is gonna give us what we call the venous, not as in the planet or the lady, but as in veins, the venous reserve, right? Oxygen that's left, right? So that we can do things like go from rest to high intensity activity, right? And not have to increase respiratory rate, right? We've got extra oxygen available if we need it, right? Sort of like having a savings account, right? If something comes up, you can dip into your savings account instead of taking a loan, right? This is the idea. And most animals follow this basic model, right? Where we have some excess in reserve, okay? The arterial blood carries way more oxygen than we need for normal rest activities, okay? And that as we increase our activity level, we increase or we pull out some of that venous reserve. We use it for that. As we go past that, okay, we increase rates of flow and things like that, all that kind of wonderful stuff. However, not every animal can do this, okay? And in fact, if you look at things like octopods, okay, so octopi, mollusks, right, that have hemocyanin, right? One of the downsides to having hemocyanin is that it doesn't have a high affinity for oxygen. It very easily drops off all of its oxygen. And so there is no venous reserve, which is what we're seeing here. So in this dark color, right, this is oxygen concentration of blood as it passes past the gill, okay? And here in the lighter purple down here, this is venous blood, basically. This is deoxygenated blood. And what we're seeing here is that in the venous blood, there is nothing left. They use up all of that oxygen. And so if an octopus is going to increase its activity level, it has no choice but to increase ventilation rate and flow rate. It cannot do anything else because it has no reserve, which puts, you know, some limits, of course, on what it can or cannot do. Going back to kind of a generalized delivery curve here and to some of the things that we touched on before, because the curve is not linear, right, we see that changes in partial pressure, right, in say the surrounding fluids, depending on what the concentration is in the blood, right, depending on where we're at in terms of that partial pressure, we might see very, very small changes in oxygen concentration in the blood, or we might see bigger changes, right? So if we're still within, say, this first, so anywhere from, say, 5 kPa up to, say, 12 kPa, which is most of our range here, right? 7, it's a little over half of our range. As long as we're in that range, we're not really dropping off a lot, right? We're still thinking about that 75% venous reserve kind of saturation, right? But as we continue to go below that, right, as tissues in your body use up more and more and more oxygen, right, the partial pressure in those tissues drops lower and lower and lower and lower, right? And as we get, say, below 5 kPa, right, we see bigger and bigger deposits or dropping off or disassociation of oxygen from the blood into those tissues with relatively small changes in partial pressure, okay? And the idea here, right, is twofold. Number one, we have this wide range of kPAs, of partial pressures, where we basically drop off 1 or no oxygens, right? Sort of our at-rest model. But when we need it, right, when tissues are going above and beyond that resting level, this ensures that we can actually drop off oxygen to them. The tissues that need oxygen are the tissues that get it, okay? Now, one of the dangers that we've got, and one of the reasons that this curve gets so sharp here towards the bottom, is that we do have a critical partial pressure, okay? It's below about 1 kPa, so about here. If we get below this, right, about 10% of the original volume of oxygen, then we actually have delivery impaired, okay? And so we need to make sure that our partial pressures never drop that low. So as we approach it, we drop off more and more and more oxygen to try to keep that from happening. Now, the shape of this curve that we've been talking about to this point has been this S-shaped or sigmoid curve. And the reason that it is S-shaped or sigmoid has to do with the structure of hemoglobin, okay? Because hemoglobin has 4 heme groups in it, 4 globin groups in it, and 4 functional groups in it. We get back to something that we've talked about way at the very beginning of class called cooperativity. Right? And basically the idea behind cooperativity in hemoglobin is that if one is bound to oxygen, it makes it more likely for the others to bind to it, right? It's sort of like, hey, it's like we'll think about it in terms of this, right? One person went out and hoarded toilet paper, and then a bunch of idiots thought, oh God, I got to do that too. And so they all ran out and hoarded toilet paper, right? This is the same idea. One heme binds to oxygen, and all the 3 others in the hemoglobin think, oh gosh, I got to do this too, and they're more likely to do it. That's all this is, right? when we have only a single group, right, one binding site, one functional group, like we do in myoglobin, we don't exhibit cooperativity because we can't have it, right? And so we go from being sigmoid here, right, to being hyperbolic, right? We have a very different shape to the dissociation curve. What this means for myoglobin is we kind of take this flat part of our hemoglobin curve and we stretch it way out, right? We're basically saying that for most partial pressures, we're going to hold on to that oxygen. We're not going to let it go. But when partial pressures get real low, we're going to let it all go at once, right? And this is just how it has to work for muscles that require oxygen, right? The idea is that they're going to, as long as the muscle is receiving oxygen from the blood, myoglobin is going to hold on to it. But when that delivery becomes impaired or insufficient, then the myoglobin is going to release what it's got stored. So again, it's all about trying to mirror in some way the relationship between supply and demand, right? We need to have a reserve in place, right? We need to not just kind of fritter it away. We don't need to spend our savings account on, I don't know what you would buy, something silly. We need to hold on to it in case we need it for something big. That's really all this comes down to. Okay, so this has gone surprisingly long. So we'll come back and we'll do a second part to this video here, where we'll continue on and talk a little bit more about delivery and transport and all of those sorts of fun things.